All right, so here in Chapter 8, we are going to take a look at the introduction to t-tests. And I know that in the book it can look kind of terrifying, but it's really not that bad. Um, I'll just give you the overall concept. All we're doing here is going to compare the mean of a sample to the mean of a population, which is exactly what we did in chapters 6. In chapter 6, where we looked at the z-test using a population and a sample as opposed to an individual score in a population. The only difference here is the last part of that sentence. We don't know what the standard deviation is. In other words, we don't know how spread out the scores are of the population. And this is a phenomenon that's actually more or less common, meaning that we don't have access to an entire population of individuals. All we know is maybe their mean, or we calculate it somehow, which we'll talk about a little bit when we get into dependent samples t-test. So in this chapter, we are covering two tests, the single sample t-test and the dependent samples t-test. For the purposes of the final project, we aren't going to use a dependent samples t-test because it creates some trickiness about getting data and the data being meaningful and everything. So we're going to focus on single sample t-test for class purposes, but I'm still going to go over the dependent samples t-test in this presentation so that you have some kind of understanding of how it works and how it's related to the single sample t-test, because these two are related. So if you're going to focus on something, focus on the single sample t-test. That's what you're going to need to know for the final project. We won't be using the dependent samples t-test, even though it's a fairly common and easy to do test. So let's go ahead and jump right into this chapter. I'm going to start by kind of giving you an overview of some of the differences between the z-tests and the t-tests. In a z-test, we are comparing a sample to a population, and we know the population's spread of scores, so we know the population standard deviation and variance, and we also know the mean. For a t-test, we know the population's mean, but we don't know what the spread of scores is. So we have some differences in the 5-step hypothesis testing procedure. The first step is the same. We're still going to declare the research question, the hypotheses, and the populations, or the groups that we're interested in. In step number 2, there is a small difference in how we calculate, but meaningful. It's small but meaningful. Difference in how we calculate the spread of the comparison distribution. In step number 2, we determine the characteristics of the comparison distribution, which is based on the population. In both cases, we need to create a distribution of means, because in both cases, we're comparing the mean of a group of scores to a distribution of individual scores, which is not a fair comparison. We learned in chapter 6. So for chapter 8, or for the any chapter on t-test, we need to create a distribution of means using a different formula to calculate the spread of the scores. So it's a difference variance formula. Here I listed as a standard deviation formula, which is just fine. So in a z-test, we know what the mean is and we know what the spread of the scores is. The population standard deviation, or sigma, is calculated as the square root of the sum of the squared deviations divided by n. So it's the sum of squares divided by the number in the sample, number of the population. For a comparison distribution for a t-test, we don't know what the spread of the scores are. We know what the mean is, but we don't know how spread out those scores are. So we can estimate how spread out the scores in the population are by using the sample information. And we'll go over the logic of that in just a moment. But the sample comes from the population. So it stands to reason that we can make an estimation of how the population looks based on the sample. We calculate the estimated population standard deviation, so we can estimate the spread of the population by using this new formula, and it's barely new. There's only one small difference to it. The symbol for estimated population standard deviation is capital S. So when you're using a t-test, we're going to use S as the symbol for standard deviation. And it is calculated as the square root of the sum of squares divided by n minus 1. Again, we'll look at the logic of that in a moment. We're just doing an overview for now. So we take the sum of the squared deviation scores and square them, divide by n minus 1, and take the square root of that. That gives us the estimated population standard deviation. And it's based on the statistics from the sample. We use the sample to calculate that. Another way of writing that is the square root of the sum of squares divided by degrees of freedom. We haven't talked about degrees of freedom yet, but I think I can throw that out there and we'll catch it as we go. But degrees of freedom is the same thing as the number in the sample minus 1. In step 3, it remains the same-ish. We use the z-table in a z-test to calculate what our cutoff score is. In a t-test, we can use the t-table, but we're also going to rely on SPSS to help us make the decision based on our critical values. In step number 4, we used the z-formula in z-test in order to calculate what the sample z-score was, and we said that it was the mean of the sample minus the mean of the distribution of means divided by the standard deviation of the distribution of means. For a t-test, the formula looks pretty similar. It is the mean of the sample minus the mean of the distribution of means divided by the standard deviation of the distribution of means. And believe it or not, calculating the standard deviation and distribution of means for a single sample t-test is not much more difficult than doing it for a z-test. So as you can see, in form, these two formulas are virtually identical. Step number 5 is the same. We still use critical values in order to determine if our sample's mean is significantly different than our population mean. These are the differences in the formulas for calculating the standard deviation and variance for when we have a known population parameter. So when we know what the spread of scores is and we know the information in order to create the spread of scores, in order to calculate the spread of scores. When we have to estimate the population parameter, so we have to estimate the population spread of scores, we use these two formulas. So the variance formula for a population, when we know all the population information, is written here, and then the standard deviation follows. The estimated population, or the unbiased estimate of the population variance, is listed here. And again, the only difference here is that n minus 1. You find the number in the sample, divide, and you subtract 1, and that becomes that denominator, also called degrees of freedom. Again, this is stuff that's in the book, so I'm hoping that you're leaning on that for your first bit of understanding, and then as you're following up here. So I'm not going to go over n minus 1. Hopefully you've seen that by now. And then in order to find the unbiased estimate of the population standard deviation, S, you take the square root of what you found for the variance, and that gives you the standard deviation, which is the same process as that we did for z-scores. That doesn't really change. Let's take a look at the formula and how we say it. So when we know that there's a certain population mean, but we don't know, or we don't have access to the population variance and standard deviation, we estimate it using data from the sample by saying that the unbiased estimate of the population variance is equal to the sum of the scores in the sample minus the mean squared, or the sum of squares, divided by n minus 1. So divided by the number in the sample minus 1, and that gives us our population variance. That's an estimate of our population variance. Now, I keep saying estimate, and we're going to talk about that in just a moment, but the interesting thing to know here is that because we're using the sample in order to talk about the entire population spread of scores, we are only estimating it because we don't have all the data from the population. So unless we had every single bit of data from the population, we are just making an estimate. We're assuming that the spread of the scores is a certain way, but it's going to be pretty close, and we'll see what that looks like in a moment. We use what are called degrees of freedom as a way to correct for the bias between the population and sample variance. What that means is this. When we have an entire population of individuals, let's say that there are 1,000 people that go to Olivet College, and we sampled 100 of them. And we wanted to compare that sample mean to the population mean at Olivet College. But unfortunately, we didn't have the information from everybody at Olivet College. All we had was their mean. We knew what their mean score was. We didn't know what the spread of scores was. If we take that sample of 100 people and we find what their variance is, then we can use that as a way to estimate what the variance is for the entire population. But it does it in such a way that underestimates the amount of spread. We'll look at this graphically in a moment, but what happens when we take a sample from a population is that we don't see all of the spread in the sample. The sample has less spread of scores. And when we take that estimate of the sample that we're trying to attribute to the population in terms of its standard deviation and variance, it'll be too small. We need a bigger estimate. And we do that by using degrees of freedom. Degrees of freedom are the number of scores in a particular distribution that are free to vary. I'm going to rely on you to read the book for a detailed explanation of that. But what happens when we try to take the degrees of freedom, hello, Dr. Moore. What happens when we take the degrees of freedom is that we are calculating the number of scores in a distribution that can be anything, but the last has to be a particular number. It sounds vague, and it kind of is, so let me go ahead and give you a brief demonstration. So when we talk about degrees of freedom, we are talking about a situation where it is almost always n minus 1. There will be some exceptions to that, but generally it'll be n minus 1. So let's take a look at just a brief demonstration of what degrees of freedom mean. Degrees of freedom means that if we have a mean of a particular number, so let's say we have a distribution that has a mean of 5. Degrees of freedom means how many numbers in a particular data set are free to vary in order to maintain the mean. Let me give you an example. If we had a 1 to 7 happiness scale, so we'll just have some kind of 1 to 7 happiness scale, and this is for happiness. Okay. So on our happiness scale, it's 1 to 7, and let's say that we have scores of 4, 6, 5, and something. Okay. This something number must be some particular number in order to maintain the average of 5. Now, in this particular examples, 3 of these numbers are free to vary. So degrees of freedom equals 3, meaning that these 3 numbers can be anything they want to as long as that last number is something. That last number cannot vary. Once these 3 numbers are chosen, so if whatever they are, those are the numbers that can be anything, this last number must be something in order to maintain an average of 5. And doing a little bit of math, we know that that number must be 5. Okay, so that means that 4 plus 6 plus 5 plus 5 has a mean of 5. And we know that by using our mean formula, the sum of all the numbers divided by n is equal to 4 plus 6 plus 5 plus 5 divided by 4 equals 20 over 4, which equals 5. Okay, so there's the proof. So our degrees of freedom equals 3. 3 of those numbers can vary, but the last one must be some number in order to equal the mean of 5. If we did this again, we could pick any 3 numbers that would come up on that scale. So let's say it is 6, 6, 7, and something. See, those 3 numbers can be anything, but this last number must be a particular number in order to add up to our mean equal to 5. And we could kind of solve for that algebraically. We could say, well, 6 plus 7 plus x divided by 4 equals 5, which is kind of our formula for the mean. We're just kind of doing it algebraically. You don't have to know how to do this. I'm just kind of demonstrating how we would arrive at that figure. So 6 plus 7 is 19 plus x divided by 4 equals 5. I'm going to run out of room. Sorry, I'm going to kind of go over here. Let's see, 19 plus x divided by 4. Our next step is to multiply both sides by 4. We get 19 plus x equals 20. And then we subtract 19 from each side. We get x equals 1. So this last number must be 1. Okay, 3 of those numbers can vary, but that last number is locked into a particular number. It can't vary. It must be something. So when we say degrees of freedom, we are talking about the number of numbers that are free to vary in a data set and still maintain the mean of the data set itself. We use degrees of freedom, or n-1, as a way to calculate the unbiased estimate of the population variance and standard deviation. And if you really want to know why it's n-1, it's a theoretical model that you can find. I think Khan Academy has one. You're probably familiar with that anyways. But you can Google it, and there are some models that talk about how close we can make the sample estimate of the population variance match the actual population variance when we know it. So what they did was they took a sample from a population that they actually knew the variance for, but they calculated the variance of that sample over and over and over again by taking multiple samples. And as they achieved 1,000 samples or so, they were starting to get the exact estimate of the population. So if you want to know more about that, you can certainly search it out. Let's just suffice it to say that n-1 is the best estimate of the actual population variance that we have without knowing the actual population variance. So continuing on, we know that we can use the sample information to estimate the spread of the population. If you want to go again into more detail about how this works, there's a YouTube clip that you can search out. You can copy down this link and you can enter it into YouTube. But there are a couple of different ways of looking at how this is. Now, you don't have to know this. It's interesting to know if you'd like to, but if you're feeling overwhelmed by this already, don't bother. Just be happy with the fact that we have a formula that doesn't really look a lot different from what we've been using already. Let me give you one last demonstration as to why we use n-1, and we're going to just do it kind of graphically. And when we divide, or when we use the sample information, so when we use the sample, standard deviation, and variance, if we were to use the standard deviation or the variance from the sample, which is when we use the formula sum of all the scores minus the mean squared divided by n, okay, we get some number, whatever it is. It's a number. Okay, and when we use the unbiased estimate, what we're doing is we are taking the unbiased estimate. Sorry, that should be square root. You're yelling at me again. You said you gotta use the square root. That's the square root of the sum of the scores in the sample minus the mean squared divided by n-1. Now, without doing any math, we know something. We know that if we use this figure, the number is going to be so big. Okay, whatever the number is, it's going to be the number. This number is going to be bigger. Okay, the unbiased estimate of the population variance is going to be bigger than the sample standard deviation. So if I have a sample of individuals here, no, pardon me, if I have a population of individuals here, and I have a sample of that population here, I'm going to use the formula SD equals the sum of all the scores minus the mean square divided by n, square root. I'm going to use that formula to calculate the sample, but I'm going to use this formula to calculate the population. The sample's spread is not going to be big enough. Okay? The spread of the scores in the sample will be less than the spread of the scores in the population. Look how big the population is. There are going to be many scores that are going to be further away from the mean than the sample is. When we want to calculate the spread of the scores in the population using a sample, if we divide by n-1, the number is going to be bigger. Okay, let's say that the sum of squares, let's say that the whole top of this equation is something like 9. Well, let me get my marker back out. Is 9. Okay, so let's say that for the sake of argument, our sample standard deviation, the sum of squares is 9, and let's say that there are 3 people in the group. So we would do sum of squares divided by degrees of freedom, or excuse me, so we do sum of squares divided by n. So the sum of the square deviation scores is 9, n is equal to 3. That would equal 3. And then we would take the square root of that, should be there. Square root of 3, 1.73. Lost my marker. So what I'm trying to say, the standard deviation of the sample is 1.73. The standard deviation of our population is likely to be bigger than that because our population is bigger. So our population, unbiased estimate of the population, should be bigger than that. And we know that by taking the square root of the sum of squares, which I just made to be 9, divided by n minus 1. And this, in the sample size was 3. That means I should divide 9 by 2. Let me get that in there the right way. Divided by 2, which is equal to 4.5. And if I take the square root of 4.5, that equals 2.12. So look what happens. When we take the standard deviation of the sample, we get 1.73. When we use the standard deviation of the sample, by dividing the sum of squares by the degrees of freedom, we get a larger estimate of the actual spread of scores. Now that's the mathematical explanation for it. I'm not going to say proof, but the mathematical explanation. But let's take a look at this. Let's say that, for the sake of example, this is a number line. It's a measurement of something. It could be height, weight, whatever it is. It doesn't matter. Let's say that the entire population mean falls right here. If I took 3 of these scores, let's say that I took this score, I took this score, and I took this score. The spread of these 3 scores is not as much as the entire population is, because it's not including all of the other variances. So what it's including is the spread of this score, and the spread of this score, and the spread of this score. It's not including the spread of all these other bits of information. So if I sampled just 3 people, I would be underestimating the amount of spread altogether. I would just be looking at the spread of 3 different points. What's worse is that, let's say that I took a sample and I accidentally got this point, and this point. 2 things would happen. I would only be looking at a little bit of spread because, these scores they all have the same amount of spread essentially. So you wouldn't get a vast amount of spread in those 3 scores altogether. So the average amount of spread is what it is. It's still not as much as the entire population. So when we take a sample, because let's say we don't have access to the population spread of scores, when we take a sample and we estimate that spread, we need to do it with an estimation that makes it seem bigger. And again, if you want to know why n-1 works, there are lots of models out there that prove it. We're not going to go over that. You'll have to take my word for it. But n-1, or the degrees of freedom, is the best way for us to estimate the actual spread in the population when we take something as small as a sample. Now, when we are in step number 2, boy, I'm a popular guy today. When we are in step number 2, and I know we're kind of skipping around, it seems like it comes out of nowhere, but in step number 2, we are particularly interested in developing our distribution of means. And again, when we are comparing the mean, I'll just kind of draw this in here, when we're comparing the mean of a population to the mean of a sample, we need to convert this population of individual scores to a distribution of means, a D of M. Okay? And what we end up doing is creating a distribution that, again, has a lot more peak to it. That allows for our sample's mean to actually have a chance at arriving at significance. So there's only a small difference in what we do for our distribution of means, and it's really about which kind of variance do we use. So in our distribution of means, the mean of the distribution of means is equal to the mean of the population. The variance of the distribution of means is based on the estimated population variance. So the estimated population variance of the distribution of means is equal to the estimated population variance divided by n, or the sum of squares divided by the degrees of freedom divided by n. We stick with the first option. If we were inclined to taking the standard deviation distribution of means, then we would say the square root of the variance of the distribution of means is equal to the standard deviation of the distribution of means, or the variance of the unbiased estimate of the variance divided by n. Either way is fine. Now let's take a look at just a brief example of how we would create a distribution of means based on just some random data. And we're going to also walk through the hand calculations of the unbiased estimate of the population, standard deviation, and variance. So this is just a brief example, and we have scores of 2, 4, 6, 8, and 10. It's just some random data. It doesn't matter what it is. We're going to calculate the estimated unbiased estimate of the population variance and the unbiased estimate of the population standard deviation. We do that by using the same formula, but we go with divided by degrees of freedom instead of the number in the sample. So it's the number in the sample minus 1. Our scores are lined up. We find the mean of 6. Degrees of freedom is equal to 4, and we know that because n is equal to 5, and degrees of freedom is n minus 1. So we have our deviation scores. We have our square deviation scores. We have our sum of squares, which is everything on top. And then we have our sum of squares divided by degrees of freedom, which is equal to 10. I did the math for you, hoping that you can do that at this point. We then calculate the distribution of means. And by the way, we didn't actually go to the unbiased estimate of the population standard deviation. We don't need that. We only need the variance. But we're used to seeing the standard deviation formula there. So we calculate the distribution of means by looking at the mean that's based on the mean of the population, but the estimated population, unbiased estimate of the population variance and deviation is based on the sample. So let's say for the sake of this example that the population mean was equal to 8, so that means that the mean of the distribution of means was going to be 8 as well, because we know that the mean of the distribution of means is equal to the mean of the population. The unbiased estimate of the population variance of the distribution of means is equal to the unbiased estimate of the population variance divided by n. Please don't get confused. When you're doing a distribution of means, you don't use degrees of freedom. You divide it by the number in the sample. That equals 10 over 5, and that equals 2. The unbiased estimate of the population variance was 10, which we calculated up here. The number in the sample is 5. The next thing to do is to take the square root of this to get our unbiased estimate of the population standard deviation of the distribution of means, which is equal to the square root of the unbiased estimate of the population variance of the distribution of means, which is equal to the square root of 2, which is equal to 1.41. So our new population curve would look like this if we were going to use it for an actual hypothesis testing procedure. Let's take a look at some symbols. That way we can kind of keep things straight. For a sample of individuals, the mean is big M, capital M. Variance is SD squared. Standard deviation is SD. For a population of individuals, where we know all of the parameters of the population, we have mu for the mean, sigma squared for variance, sigma for standard deviation. And in a case like in t-tests, where we know the mean but we don't know the variance or standard deviation, there is no symbol for the unbiased estimate of the population. You have to know what the population mean is, and the population mean would be mu, so it's the same thing. But there is no unbiased estimate of the population for the mean. The unbiased estimate of the population variance is S squared. Unbiased estimate of the population standard deviation is S. Now, we've talked about how to kind of develop the comparison distribution, but not so much about the cutoff scores. So when we have a t distribution or a t-test, we need to know a couple of things. We need to know what the alpha level is, which is also the critical value, the cutoff score, the p-value for the cutoff, etc. And in most cases, it's still going to be 0.05. So, but you need to know what the alpha level is or the critical value is. You also need to know the number of tails, that is one-tailed, two-tailed, that's directional versus non-directional. So far, these two are the same. There's no difference between how we indicate the alpha level or the number of tails in a t-test. But you do need to know the degrees of freedom. The degrees of freedom will help you to determine which critical t-value you have. T-scores are just a measurement of the number of standard deviations away from the mean, just like a z-score is the number of standard deviations away from the mean. The t-score, the cutoff t-score, is going to indicate how far away from the mean our sample score needs to be in order to consider it significant. For example, if we had a t-distribution and we wanted to know what the cutoff t-score was, so the number of standard deviations away from the mean our t-score needed to be in order to be significant, we would look at the column that says what our critical value is, and it's normally 0.05. Then we would go down to the degrees of freedom, which is 15, and this is just example, and you would have a t-score of 1.753. Now, keep in mind that this is just a snippet from the book. This does kind of follow an example that we're going to get to, so this will be handy for you to keep an eye on. Let's go ahead and jump into an example with this because it feels like we need to shake it all off and just kind of get into some kind of reality so that we're not mucking around too much in all of the quagmire that is determining what the unbiased estimate is and why it is and everything. So let's go through an example in a linear way and focus on this. This is what's going to be most helpful to you probably in the application of these statistics. So here we go. Suppose your college newspaper reports an informal survey showing that students at your college study on average of 17 hours per week. However, you think that the students in your dorm study much more than that. You randomly pick 16 students from your dorm and ask them on an anonymous questionnaire how much they study each week. Your result is that these 16 students study an average of 21 hours per week. We're going to use a cutoff value at the 0.05 level with one tail. And we're using one tail because we want to know if there is an increase in study or if you think that your sample studies more. So in step number 2, the population, which is our comparison distribution, is a distribution of scores with a mean of 17 hours studied in an unknown population standard deviation. We don't know what the spread of the scores is. All we know is that the mean of that population was 17. We can use the sample's information in order to estimate what the spread of the population might be. And remember, we can do that because when we take a sample from a population, they share characteristics because they do come from that population. But what we have to do is be careful to calculate it the right way using the unbiased estimate of the population variance. In order to do this, we're going to be given some information that makes the calculations a little bit simpler so that we don't have to go back and review something from 4 chapters ago. The mean of the sample is 21, meaning the people in the dorm studied on average 21 hours. The sum of squares for the sample, which is everything that's on top of the equation, right? That's the sum of x minus m squared. The sum of squares is 694. The degrees of freedom, which is equal to n minus 1, is 16 minus 1 because 16 is the number in the sample from your dorm, minus 1 equals 15. That gives us the information we need in order to calculate the estimated population variance and standard deviation. So S squared, the unbiased estimate of the population variance, is equal to the sum of squares divided by n minus 1, or SS divided by n minus 1, or SS divided by degrees of freedom, you can see that there's a lot of different ways to write this, equals 694 divided by 15, which equals 46.27. So the unbiased estimate of the population variance is 46.27. Now, you might be thinking to yourself, oh great, now we can calculate the unbiased estimate of the population standard deviation. You can, but we actually don't use that. We use the unbiased estimate of the population variance because our next step is to create a distribution of means, and we do that using the unbiased estimate of the population variance. Now that we know what the estimated population variance is, we can create the comparison distribution to see if students in your dorm study more than the rest of the college. Remember, the study has a population of individual scores, but you're comparing the mean of 16 scores to that, so we need to create a distribution of means in order to create a fair comparison. So in this case, the mean of our the mean of our population is equal to 17. And the rule states that the mean of the distribution of means is equal to the mean of the population. So the mean of the distribution of means will be 17. And we're going to look at that in a moment. The estimated population variance of the distribution of means is equal to the estimated population variance divided by n, which is 46.27 divided by 16, which is equal to 2.89. Remember, we're not using n minus 1 here. We only use that when we're calculating the unbiased estimate of the population variance. We use n when we're calculating the distribution of means. The next step is to calculate the unbiased estimate of the population standard deviation of the distribution of means, which is equal to the square root of what we found in the second rule. So the square root of the unbiased estimate of the population variance of the distribution of means is equal to the square root of 2.89, which is equal to 1.70. So what's going to happen is that our new distribution is going to have a mean of 17, but instead of having a spread of 6.8, it's going to have a spread of 1.70, which looks like this. So our new comparison distribution has a mean of 17, so a population mean of 17, and an unbiased estimate of the population standard deviation of the distribution of means of 1.7. So now that we have a comparison distribution, let's take a look and see where our score needs to fall on the comparison distribution. Oh, one last thing. I included the t-score. So the t-values are, remember, this is the same as a z-score. It's the number of standard deviations above or below a mean. So we're going to measure our cutoff score in terms of its t-score, how far away it is from the mean. In step 3, we need to decide on the critical value, or the t-value, it's the same thing, where we will choose to reject the null hypothesis. So we're going to find the t-value, or the t-score on our comparison distribution, where we will reject or fail to reject the null hypothesis. We need to know 3 things: significance level, the number of tails, and the degrees of freedom. The significance level is given to us in the example. We want to know if it is significant at the 0.05 or the alpha level equal to 0.05. Number of tails is 1. Remember, we're interested in an increase in study time. We think that our sample will have a greater study time. And the degrees of freedom is equal to 15. N minus 1, which is 16 minus 1 equals 15. Our alpha cutoff, or our alpha level, our cutoff t-score, or our alpha level, same thing, is equal to 1.753 according to our t-table. And if we look at our distribution, our cutoff t-score is identified by the red dotted line, which is equal to approximately 1.753. So if our sample's t-score is above 1.753, then our result will be significant. We will reject the null hypothesis. Or if it is less than our cutoff, or equal to our cutoff, then we will fail to reject the null hypothesis. Step number 4, we're going to calculate the sample's t-score on the comparison distribution using the usual formula. And I wanted to throw the graphic in there as well to kind of help you understand what we're looking at here. So we're going to use the formula t is equal to the sample mean minus the mean of the distribution of means divided by the estimated population standard deviation of the distribution of means, which is equal to 21 minus 17 divided by 1.7, which is equal to 4 divided by 1.7, which is equal to 2.35. Here's what we see here. Our population has a mean of 17. Our comparison distribution has a mean of 17, with a standard deviation of 1.7. And our t-scores are identified here, where you have a t-score of 0 means it's on the mean. One standard deviation is one t-score. Two standard deviations is two t-scores. Our result is at 2.35 t-scores above the mean. Let's take a look at step 5 and see what it looks like. In step number 5, we have that our population is less than or equal to our population 2, which is our null hypothesis. Remember, we're always testing the null hypothesis to see if our sample is different than a situation where there is no effect. So if there is no effect, population 1, so our sample score would be less than or equal to our cutoff score, population 2 score. Hopefully by now you understand that we're talking about sample t-scores or z-scores compared to cutoff t-scores or z-scores. So we plug in our t-scores for our sample, which is 2.35. Then we plug in our cutoff t-score that's based on the comparison distribution of 1.753, where we said that we would reject or fail to reject the null hypothesis. And we ask this question: is 2.35 less than or equal to 1.735? The answer is no. So if this is not true, then we reject the null hypothesis. We are rejecting this hypothesis in favor of the alternate hypothesis. So we reject the null hypothesis, which means that we have a significant increase in our studying hours. In this chapter and going forward, one of the tasks that we have is to create an APA results section. And it's a very short paragraph with only 3 sentences that totally encompasses the results of your study. Here's that result statement as you would need to write it for your data analysis. A single sample t-test was conducted to determine if students in a dormitory studied more than other students at a college. There was a significant increase in the hours studied between the students in the dormitory, M is equal to 21, and the other students in the study. The population mean is equal to 17. You had a T of 15 degrees of freedom equals 2.35 with a P equal to 0.016. These results indicate that students in the dormitory study significantly more hours than other students, which suggests a rejection of the null hypothesis. That's it. Something you may have noticed, though, is that I said P is equal to 0.016. When you're using SPSS for your data analyses, it will tell you exactly what the probability of your result is. In this case, we wanted to see a P less than 0.05. Our result, our sample's t-value, occurs 1.6% of the time on the comparison distribution. So only 1.6% of the scores are greater than the studying hours of 21 based on our comparison distribution based on the population. You would not be able to figure that out on your own, so that's why the asterisk is there. It will be told to you through SPSS, or if you were clever enough to find a P calculator, you could have found it out too, or using the t-table. But based on what we've talked about so far, you wouldn't be expected to know that from the example in the book. Now, when we use SPSS, the guide will tell you where to get that information from. So at the beginning of the session, I think that I said that we were going to get to dependent samples t-test. I'm not even going to cover that right now. This lecture has gotten really long, and I don't want to go into it right now. If we do cover it in class for any particular reason, which is super unlikely, I will create a video that will cover that separately. But I think that we've gotten into enough today to make sure that you understand this stuff or have the opportunity to understand it. Review some things, and what I want you to focus on is that example that we just went through, the 5 hypothesis steps. That helps to give you a more global perspective on what we're doing as opposed to getting bogged down by the calculations. So please focus on the big ideas. We go through the tedious aspects of it to give you an understanding of how it works mechanically. I'm much more inclined to being impressed by your work on the data analysis, which is more based on interpretation and setting up the example rather than the hand calculations. So please focus on what you need to do for the data analysis, even though this is important stuff for you to be able to see and be familiar with, but focus on the data analysis and you're going to do much better. So I look forward to what you can do with the data analysis. If you have any questions, feel free to reach out.